The objective is to design a smart neuromorphic satellite platform that integrates neural networks and deep machine learning mathematical algorithms. Intelligent satellites, distributed artificial intelligence via neuromorphic architectures, embed complex mathematical AI algorithms for swarm autonomy and distributed computing, intuitive and decision-making for spacecraft and/or cluster nanometer-based small satellites. The machine learning neural networks enable the satellites to solve communications issues and self-corrective action to avoid collision and any other problem currently unknown to space travel and/or space orbits. This video illustrates a design of a satellite constituted by several subsystems: attitude, determination, and control subsystem, telemetry tracking and command support, guidance and navigation embedded, power and thermal structure, artificial intelligence, cognitive and intuitive neuromorphic architecture, and machine learning algorithms, performing autonomous actions to determine its own health and status, and with artificial intelligence able to make decisions on the enhanced cognition and self-awareness. A satellite constellation is a group of artificial satellites working in concert. Such a constellation can be considered to be a number of satellites with coordinated ground coverage, operating together under shared control, synchronized so that they overlap well in coverage. The period in which a satellite or other spacecraft is visible above the horizon. Low Earth orbiting satellites are often deployed in satellite constellations because the coverage area provided by a single low Earth orbiting satellite only covers a small area that moves as the satellite travels at the high angular velocity needed to maintain its orbit. In this application, the telemetry is used by the unmanned satellite spacecraft for data transmission because it needs to collect data from distances of more than 500 kilometers, even 10 billion kilometers have been covered, such as some American spacecraft that we have deployed in space. Therefore, telemetry is essentially an automated communications process by which measurements and other data are collected at remote areas such as orbital space, where points of information are inaccessible, in the environment. Here I use a telemetry subsystem, which is vital in the development of satellite systems, because the system might be destroyed during or after a test. So engineers need critical system parameters to analyze, that is to improve the performance of the system as it is deployed in orbital space. In the satellite spectrum, using Kepler's laws of planetary motion and Newtonian mechanics, the exact conditions are used for putting satellites into geospace and stationary orbits. The inertial measurement unit used in this satellite measures and reports orientation, velocity, and gravitational forces through the use of accelerometers, gyroscopes, and magnetometers. The gyroscope is used for measuring and maintaining orientation and also angular velocity. It is a spinning wheel or disc in which the axis of rotation, which is the spin axis, is free to assume any orientation by itself. When rotating, the orientation of the axis is unaffected by tilting or rotation of the mounting according to the conservation of angular momentum. The inertial measurement unit detects linear acceleration using several accelerometers and rotational rate using several gyroscopes, which also includes a magnetometer, which is used as a heading reference. The intelligent satellite software platform consists of complex mathematical algorithms, sophisticated software models, and artificial intelligence modules. The main objective is to provide the control environment for the telemetry, the gyroscope, and the magnetometer subsystems, as illustrated in this engineering prototype, as shown in this video.